So, yeah, the bijective function video is gonna have to be a part 1 and part 2. The part 1 is gonna be mainly definitions and I think just one example. And part 2 is gonna be examples to really understand what's going on. So, yeah, there's gonna be a part 2. Okay, I'm kind of curious to see how much this is gonna take. So I'm doing it right after the next video, right? Okay, bijective functions. Well, that's the goal, really. Well, the goal really is just to get to maybe inverses, but they're really tied together, right? Okay, so like I said, here in this video, I'm gonna do mostly definitions and maybe a few examples, right? Let's get to it. Definitions. Okay, let's f go from a to b, right? Be a function. Okay, suppose capital C is a subset of A, just any subset. Then we define this set right here, f of capital C, as just the outputs, all the outputs from C. Too many C's, huh? But yeah, so if f goes from A to B, meaning that we know that everything in A goes somewhere, right? And then suppose we look specifically at some subset of A, right? Then we're gonna call this the image. Oh yeah. So we call this. So this is the parentheses, well, quotations, the image of C under F. Okay. Now, again, right? F goes from A to C, so this thing is again, it's all outputs, right? So I just want you to note that this set, it's a subset of B. Okay. Definition. Well, again, right, I'm saying, so if a subset of A, where does it go? Well, we're calling it goes to this place called f of C, right? Well, what about the other way around? Suppose now that you have a subset of the codomain, and you're trying to trace back where the elements that map to it, right? So let f again be from A to B, be a function. So then now suppose that capital D is a subset of the codomain. Then we're gonna say that this set f inverse of D is basically, again, exactly what I said, all the elements in A so that they get mapped into D, right? So then now we call this the preimage. So this is the preimage of D under F. Now, funny thing is that you might be looking at this thing and be like, oh, that's F inverse, right? So we gotta be careful, right? This right here right now just means, again, preimage. So yeah, it kind of hints at that it's supposed to like undo, right? But so at this point, no, we don't have an inverse function yet, and we're not applying, again, right? In here we have a set from a subset of A, to which we are applying this function f, right? So you might be thinking, you might look at this and you think, oh, f inverse d, oh, that clearly has to be that this function f inverse already exists and we're just applying d to it. But that's not what it means. You know, they are different. They're being defined differently, right? So again, fc is just all the outputs from all the c's and c's, but the preimage is all the elements in the domain that just happen to get mapped into d. And then another quick note. Well, you can see it from here, right? In the same way that f of c is a subset of b, the preimage is a subset of a. Okay, so in case you forget, you know, every time you look at f inverse of something, you gotta think, oh, the elements here are actually inputs. And then, but if you see f of c, then you think, okay, these guys are outputs. You know, that's what it means for being a subset of b. That's what it means for this to be a subset of a. Well, okay, what does this mean, right? Let's do an example. This is probably gonna be my favorite function that I'm gonna keep using, right? Let f from real numbers to real numbers be f of x equals to x squared. Just because I feel like everyone knows a lot of things about the what do you call it again? Parabola, right? So this function looks like this. So again, let's say that 1's right here, and then I don't know, let's say that 2 is right here, right? If I say, you know, so again, right? By the way, okay, so 1 comma 2, right? It looks like that, right? I think I said this before, that, you know, it's kind of unfortunate, right? But again, this is an interval, right? So if you don't know, let me just write them on the side, right? An interval a comma b, right, with the brackets, it just means all the x's in real numbers such that the x, so if I use a bracket, then I'm saying that, so x is greater than or equal to a, but x is also less than or equal to b. And if instead of using brackets I use parentheses, and this is the part that's unfortunate, right? Because you think, oh, that's a coordinate. It's just unfortunate that it come out this way. If you're saying a comma b is an interval, you gotta tell somebody that it's an interval. Then this is just all the x's in real numbers such that. So parentheses means that now the inequality is strict, meaning not equal to. You know, and then you can mix and match. You could do like bracket here but open here. It's gonna mean exactly what you think. So because the bracket is with a, this one gets a less than or equal to, but then because it's a parenthesis here, this one gets a strict b, you know. And again, you can kind of figure out what that open a but bracket b is. I guess I'll just do it. Right, so on, you know, so on and so forth. So for example, 1 comma 2 is a subset of the domain, right? It's an interval, right? So the image of 1 comma 2 is basically, you know, the outputs. Where do all these values go, right? Well, you know, 1 is gonna go to 1. 2 is gonna go to, let's say, 4. And everything in between is gonna go to everything in between. You know, more or less. So then the set, the outputs is gonna be between 1 and 4. Okay. Okay, but then see what happens here. This thing is kind of interesting. Suppose you're now asking for the pre-image of 1 to 4. You know, so again, what's the pre-image of 1 to 4? It means all the x values if you take it from the definition, right, it's going to be all the x values in the domain, which they happen to be the same, such that f of x lands in 1, 4, right? So the funny thing is that, yeah, every single element here lands in 1, 4, right? But then the funny thing is that if you know, -1's right here, and then -2 is right here, well, the same thing happens over here. That all of these x values also go to 1, 4. You see that? Every value here also is going to go between 1 and 4. So then the pre-image of 1, 4 is going to be both this strip of the x-axis and of course this strip of the x-axis, meaning the pre-image of 1, 4 is -2 to -1 union 1 to 2. So the image of 1, 2 under f is 1, 4, but then the pre-image of 1, 4 under this function f is actually not that. It actually got something bigger, right? Well, damn, right? It's kind of unfortunate, right? You would have hoped that maybe it was the same thing, but it's not. Another thing is that, again, right? The funny thing about this function is that it doesn't touch any negative numbers. So, for example, if I said what's the pre-image of, let's think in terms of the y-axis. You know what? Just from -infinity to just 0, but not including 0, right? Which is just, again, all the negative numbers, strictly all the negative numbers, right? Well, again, right, there's no x value for negative numbers. The way that you trace is that you're supposed to go from the x-axis to the picture, to the graph, right? So in this case, you can only go up because the graph is only in these two, in this quartile and in this quartile, right? You know, meaning you can never get any negative numbers. So the pre-image of this set is really just asking what are the real numbers such that basically x squared is less than 0, which is negative, right? Well, as you're seeing there, yeah, there's no way that never happens, right? If x equals 0, then x squared equals 0. But if x is negative or positive, x squared is always positive, right? So if you're thinking, oh, well, what happens here? Well, I just want to tell you, you don't have to freak out. This is just the empty set. Okay. Meaning that, yeah, there are no real numbers such that this happens, right? So just keep that in mind. You know, if no element in the domain maps to whatever thing that you're looking at, then yeah, that's completely fine. You just say, well, okay, there's no elements. So why did this happen? The reason why this happens is because, well, I keep saying this, right? The only y values that are being hit by this function is either 0 or positive numbers, right? Well, one way to put that is the following: f of real numbers, meaning the image of the domain, in a way, in this particular case turns out to be 0, infinity, you know, meaning 0 and positive numbers. So that's why this other set, which is just strictly negative numbers, doesn't have a pre-image at all, you know. Well, that's kind of important, you know. Let me. This thing has a name, definition. It has a name that you've heard a lot. You just probably didn't see it that way. So let f go from a to b be a function, right? So let f from a to b be a function. Well, the entire image of a even though, yeah, we defined it here, right? I mean, obviously A is a subset of A, so there's nothing wrong with you know, there's nothing wrong with me saying f of A, because, you know, A is a subset of A. I mean, every element in A is also in A, right? But this guy in particular, right, if f is a function from A to B, we call f of A the range. The range of f. So again, you know, sometimes you hear in math class, you know, what, give me the range of this function. Well, in math class they ask you for the domain and the range, right? Well, the range is just in particular all the y values that are being hit by your function, right? There's no other way to look at that other than just the image of the entire domain, right? So yeah, the image of the entire domain is the range, which is also all the y values that are being hit by your function. Well, okay, let's continue. Let me add more definitions. Let f from A to B be a function. We say f is surjective, which is another word for onto. If all definitions are if and only if, by the way. So what needs to happen for a function to be surjective or onto? If let me see, for every b in B, there exists an A in A such that B equals f of A. Okay, so what am I saying here? I'm basically saying that for everything in the codomain, for every y value, if you want to think of the way, there has to exist some x value that maps to it. Meaning, if a function from A to B, if we call this function from A to B to be onto, it means that everything, absolutely everything here is being hit by at least something in here, right? So another way to put that, so note, another way to put that is basically the following. So f is onto, you know, surjective, whatever. Basically, if the range is all of B, right? If the range is completely the entire codomain, then that's what it means to be onto. Okay, I'm doing pretty good in time, seems like, so I'm glad about that. Okay, so let's talk about this, right? I can't help to feel like, you know, there was something here that was a failure, right? Let's say that 1 comma 2 is some subset C, right? So f of C was like some other set D, but f inverse of D was not back to C, right? It was something else. So what I'm saying is that hopefully, right, if we want to say that we want to find a function that undoes what f does, right? So we would hope that f inverse of f of C would come back to just be C, right? Okay, well, maybe we don't even want that. Maybe we just want, to the very least, so to the very least, we want that to undo that, right? That f inverse of f of A equals A, right? Right. So what do we have? What conditions do we need so that a function does either that, or to the very least it does that f inverse of f of A equals A, right? Well, why did it fail here, right? What happened here that was so wrong? So back to f of x being x squared, right? Well, I think this is what happened, right? Since, let's say, f of 2 equals 4, but 4 also happens to be f of negative 2, right? Again, what am I saying? 2 comma 4 is an f, and also negative 2 comma 4 is an f. And again, if you remember the last video, right? The fact that these are different inputs but the same output, that's actually not forbidden, right? That's not prohibited. That's why f of x equals x squared, yeah, it's a function, right? But yeah, right, the fact that this is not forbidden, I think, is the whole problem, right? Because here's why I think this is a problem. Suppose that we wanted to undo 4, right? Is f inverse of 4 equal to 2 or negative 2? Right? That's the question. The fact that since f of 2 and also f of negative 2 go to 4, right? If you want to undo it, how do you undo it? Do you go with 2 or do you go with negative 2, right? How do you pick favorites? Well, okay. Here's a definition. Let f go from a to b be a function we say that f is injective, like you're getting an injection, right? Injective. So injective is another word for one-to-one. Maybe I should put hyphens, one-to-one. If we want to kind of avoid something like that, we say something like this, If two inputs are different, right? So if, I don't know, x1 is not equal to x2, if two inputs are different, then their outputs are different. F of x1 has to be different from f of x2. Okay, so we're saying that a function is injective or one-to-one if different inputs give you different outputs, right? And so at this point you would think, a function, I feel like, should have done that from the beginning, right? But no, right? A function is just an assignment. It's a mapping. It tells me, okay, if you have a bunch of real numbers, where do they go to, right? So all you have to do is trace the picture, and it tells you which y value goes to, right? This is a more special type of function, right? This is a special where, okay, as long as the x values are different, the y values will also be different, right? Now, so that's what's injected, right? The only thing with this is that it's actually not that helpful mathematically to look at it like this. So for now, I'm just gonna tell you to believe this. So this is a fact. The statement, if x1 is not equal to x2, then f of x1 is not equal to f of x2. This statement is equivalent to the following statement. If f of x1 equals f of x2, then x1 equals x2. So yeah, I don't know. You can kind of maybe try to break your head around that, but yeah, the statement, if x1 and x2 are not equal, then f of x1 and x2 are not equal, is equivalent to saying that if two outputs are the same, then the inputs are the same. Maybe that's one way to look at it. And that's what it means for a function to be one to one. This next definition, I might as well give it to you because it's just like, it just follows from what I just said. Definition. We say f from a to b, function, is bijective if and only if f is both injective and surjective. So we finally made it to what a bijective function is. I guess I should. Right? So a function is bijective if it's one-to-one and onto, if it's injective and surjective. Alright, so why do I keep saying, okay, a function needs to be bijective to have an inverse, right? We want, f inverse as a function to undo f, right? Meaning that, for example, if f of 3 equals 5, then hopefully f inverse of 5 equals 3. That's what we want. That's what we mean by undo. Okay. Now, if f goes from a to b, right, and you can think of this 3 as the little a and the 5 as the b, right? So then now f inverse of 5 equals 3 means that we're plugging in the b and getting the a back, right? So right from the get-go, it means that we want f inverse to go from b to a, so that if b happens to be equal to f of a, then f inverse of b equals a. Well, if we want f inverse to be a function, right? Here's the key thing, right? If we want f inverse to be a function, well, it only needs to pass two criteria, right? It needs to pass that for every element here, it's gonna go to somewhere in A. Right? So how do we know that's guaranteed, right? Well, if f is onto surjective, right? Again, it means that then if b is in b is going to be equal to f of a for some a in a, right? So if f is onto, then pick an element here, right? If you go back to the definition of onto, it means that if f is onto, it means that for every element in b, there's some a that maps to it. So yeah, right, for every element in b, right, there's gonna be some element in a, so that b equals f of a. So then what does that mean? Then f inverse of b is just gonna go to a, right? So So it means that it's gonna go somewhere, right? That's the first condition. The second condition is that it's well defined, right? How do we know that it's well defined? So how do we know that f inverse of b goes to only one output, as you can say, right? Well, that's actually just exactly what one-to-one means. Well, okay, suppose that b1 is equal to b2, right? So the two quantities, they might look different, but they're equal in value, right? How do we know that it's well defined, right? We want that f inverse of b1 equals f inverse of b2, right? That's what we want, that the f inverse function itself is well defined. Okay. Well, okay, so look at this, right? Like I said, b1 is in b. So let's say that there exists an a1 in a, so that, well, it doesn't matter, but I'll write it anyways, right? So that b1 equals f of a1, right? Well, okay, b2 is also the same thing, right? b2 is also in b, so maybe there's a a2, not necessarily the same element, right? There's an a2 in a, so that b2 equals f of a2. Okay, so again, right, so these two quantities are equal, but they might look different, right? Well, the fact that b1 is in b means that I know there's an a1 in a that maps to it, and because b2 is in b, same thing again. I know there's an a2, so that b2 equals f of a2, right? But okay, if b1 equals b2, so f of a1 equals b1, and we're assuming that b1 equals b2, so b1 equals b2, but b2 is f of a2, right? What am I really saying? I'm saying that f of a1 equals f of a2, right? And that's why I said that the injective part, a function is injective, means that if f of a1 equals f of a2, it must be the case then a1 equals a2, right? But again, look at this, right? If b1 equals f of a1, then that has to mean that f inverse of b1 equals a1, right? Similarly, if b2 equals f of a2, that has to mean that f inverse of b2 is gonna go to a2, right? So what I'm saying, that just from this fact alone means that the inverse needs to map b1 to a1, and then just from this fact alone, it means that the inverse needs to map b2 to a2. Luckily, I just show that they're equal, right? So if a1 equals a2, then that means that f inverse of b1 equals f inverse of b2. So I ended up doing a proof, kinda, right? Maybe I didn't really need to do the proof. That was what one-to-one meant, though, isn't it? That different x values give you different y values, right? So why does f inverse b goes to only one output? Well, that's because if f is one-to-one, if f is injective, 1-to-1, again 1-to-1 injective, right? If f is injective, then yeah, f inverse of b can only go to one value. Well, anyways, I kind of fell apart at the end, right? And I know that the time is probably too long, so yeah, like I said, I'll probably, so we're not done. I mean, we're barely getting into this fact. We're barely getting to say that if f from a to b is bijective, then it suddenly has an inverse function, f inverse from b to a. That is supposed to undo it. I mean, let me just say that real quick. If f a to b is the bijective function, then f inverse goes from b to a is a function. We define f inverse. So if I define it as a set type of function, right? If f inverse is going to be the set of b comma a in b cross a, right? With the added condition that b has to be equal to f of a, right? So this is saying that my inverse function is going to take the elements b to the element a only with the condition that b equals f of a. So this is very important. I'm saying f inverse of x equals to y if and only if x equals f of y. Okay, so yeah, that's the connection, right? Where does b go? Well, you have to know where b came from in the first place to know where it goes. You know, we say that b goes to a because b equals f of a. I really want to do an example, but that's going to be what part 2. Part 2 is just going to start with me doing examples, because like I said, believe it or not, I have like 1 page left on my supposed plan mapped out outline, so I'm guessing it's going to take about 30 minutes, right? Let me know what I could explain better, because again, I'm pretty sure I kind of dropped the ball at the very end. Some suggestions, some things to note. You know, I want to hear from you, but I'll leave it like this in this video. See you in the next one.